Great. So today I was asked to give an overview of my lab, the Robomechanics Lab at Carnegie Mellon. And in my lab, we're really interested in taking robots out of the lab, out of the factory, and into the real world. And of course, the problem with this is that the world is a mess. And so whether we're talking about natural terrain or man-made environments, once we no longer can polish the floor to be perfectly smooth and level, even things that we think of as being very regular, like staircases, this is what staircases look like in Pittsburgh often, are sort of just as messy as the natural world. And the same is true for both locomotion and also manipulation. So this was my dorm room freshman year. Manipulation and clutter is a very messy task. So what are some of the problems that come up? So here's a video from my PhD work taking Rex out into the Mojave Desert. And this is sort of the blooper reel that we put together. And in all of these, the robot seems to be doing pretty well. It's kind of bouncing over some rocks. And then one leg just gets stuck on a rock in a weird way. So, and all of a sudden the robot pitches or rolls out of the way, flips over. And so we see when we were out there, almost all of the failures really came from this kind of unexpected ground contact, either with the leg or with the body, as we're running along. And so this is true for robot locomotion. It's also true for human locomotion. Someone showed this video last year. This is at Dynamic Walking. This is New York City subway stairs, where over time the stairs have settled so that one step in the middle is slightly taller than all of the other ones. And we as humans don't have, sub-millimeter laser eyes or whatever. And so we don't notice this, and we walk along and we stub our toe on the stair. And almost everyone that comes up the stair trips as they're going. So some of the key challenges that we look at in my lab are pulling from these two ideas of the challenges that come from contact and uncertainty. In particular, how these two things interact. And so contact is an inherently discontinuous process. So when my finger is just above the surface, I get zero contact force. As soon as I can touch the surface, I can have large amounts of contact force. And so this creates a lot of problems because most of the tools and methods we know for analysis, for control, for optimization, they assume smooth, if not convex or linear or like very, very smooth systems. And then on the uncertainty side, maybe we can put together a pretty good model of our robot. As Jeff mentioned, that's often pretty hard actually. But we're never going to have perfect models of the rock field in front of us and which rocks are loose. And once we start sort of interacting with an unknown part of our dynamics, namely the environment, we're going to have significant amounts of uncertainty, both state uncertainty as well as model uncertainty. And so what is the name Robomechanics Lab? Why did I come up with that? So this is sort of calling back to the field of biomechanics, which of course many people here are experts in. And in biomechanics, the idea is to study animals and their dynamics and kinematics to see how they move. And so in my lab, we do the same thing, but with robots. So even though we may be built or programmed the robot, we're still sort of studying it like it's a creature that we don't understand. And then in this context of pushing robots into the real world and contact and uncertainty, we sort of work on all areas of robotics. And so hardware design, software design, sensor feedback, as well as modeling these different environments that we're going into, in addition to sort of system level behaviors of interest. So today I thought I'd go through and give examples in each of these different areas, but I'll spend most of my time talking about controller design. And in particular, I wanted to go a little bit deeper on trajectory optimization. So we do lots of different control and learning in my lab, both learning with the actual robot in the loop and then learning using modeling and simulation. Today I'm going to focus on trajectory optimization and again looking at how contact and uncertainty can play into this kind of formulation. So how do we generate a trajectory or generate a controller that has many different contact conditions? So for instance here, let's say we threw this ball at the ground, it slid along, and then it went up the hill. How do we sort of generate these kinds of motions? And so one option is to decide ahead of time which contacts will occur and in which order. And so we might call this the hybrid trajectory optimization formulation. We're going to take our trajectory, break it up into smaller finite elements. We'll say the first few finite elements were going to be in the air, and then the next few were on the ground, and then the next few were on this hill here. And now in each contact mode, we can write down the dynamics and it's actually the same within the mode as a smooth trajectory optimization problem. The only difference is that now we have to piece these together with some kind of impact law to handle our transitions between these different continuous phases. And so what does the output of this kind of hybrid trajectory optimization look like? So here are some acceleration, deceleration, and bounding results with the robot. Why are we running these results, and why is there a tail in some of these animations? My student Joe has a poster here. Poster's right there. He's giving a spotlight later today. Let's see, Joe Norby is over there. Go ask him why we put this tail on and doing these weird jumps. For now, this is just the output of a trajectory optimization. For some reason, we asked for this, and this is the output. And in particular, for these behaviors, there's only a few different contact modes, and there's maybe 2 or 3 options for what the sequence of contact modes would be. And so we can simply run all of the different possible sequences and take the best result. But what if we can't specify the contact sequence? What if it's too complicated behavior to know what was going to be touching where? And so this brings us to the idea of contact invariant trajectory optimization, which goes back to Poza and Igor Mordach and others. And the idea with contact invariant trajectory optimization is that every point along the trajectory, we're going to allow contact forces from all possible contacts in the environment. And so then to sort of constrain this to be physically realistic, we have to add in complementarity constraints that say, if you're actually going to use the force from this contact point, you'd better be actually touching it. The complementarity says that either the distance needs to be 0, in which case you can have some force, or the force needs to be 0, and you can be somewhere else in the environment. The other thing to note with this kind of contact invariant framework is that we're going to combine forces and impulses together. So over the course of a finite element, we'll think about the cumulative effect of interacting with that contact point. And this lets us avoid having to have these impact laws in between different phases. We're just going to lump it all together and let the system add and remove contacts however it needs to. So what's the problem with contact-implicit optimization? So far, they've been limited to Euler integration, meaning first-order integration. And so you can think of this as we have these individual time steps, and then within the time step, we don't really know when we're touching down, when we're lifting off, and we don't actually care. And the problem with the Euler integration is it's very low accuracy. The advantage is that in some ways it's kind of discontinuous everywhere. Right? So we're sort of piecewise linear. Every single segment, we can be going at a different velocity. And so if we have lots of impacts, this is fine because we're already discontinuous everywhere. In fact, here's a quote, if no collision detection is performed, the integration method cannot exceed order 1. And so the intuition here is, let's say I'm trying to fit a higher order curve, like a cubic or higher order polynomial, to something that's either non-smooth or even discontinuous. Right? So trying to fit this smooth curve to something that's not smooth is going to be very hard. So this idea that we can only use first-order integration, this is actually true for simulation. So if you're using this kind of method for simulation, it's called time stepping. It has to be first order, but it's not true for optimization. And so we show in this recent Robotics Automation Letters paper that if we constrain the contact changes to be at the boundary between finite elements, then we can have smooth curves within a certain contact mode, contain these discontinuous events to the boundary between these finite elements. And in doing so, we're including now the time of these events in our optimization. So the optimization is solving for positions, velocities, contact forces, but also the time of each of these finite elements. And in that way, that the optimizer is actually solving the collision detection problem for us. So it's doing the collision detection. We can use these higher order methods. We have a constraint that you can't go through the surface. Then that would be an infeasible point, and then the optimizer would shift the trajectory or shift the times around so that it lines up. So what's the sort of output of this kind of contact-implicit method? Here we've taken a 5-link biped model. We've asked it to run 10 meters, and there's a 1 meter gap in the middle. We call the gap a snake pit for some reason. And you can see here that there's many contacts going on, so it's heel-toe on each foot. In the middle, it's actually up on its toes sprinting. At the end, it does this little bunny hop to stop really quickly. And so it would be very hard to write down what the sequence of contacts should be for this kind of problem ahead of time. Here, I'm showing the comparison between first-order methods, so this is sort of traditional contact-implicit trajectory optimization, with our higher order. And you can look at the error numbers. We can measure how much better we're representing these dynamics. But I think qualitatively, you can really see that the top solution, which is technically feasible according to the problem formulation, looks like it's sort of exploiting some weird quirks in the dynamics, and it doesn't look very natural. Whereas the higher order, smoother dynamics have a much more realistic looking result. Yes? So we constrain that if you, that's not a quick question. Yeah. I left all the math out of that section, so it's harder to answer that, yeah. Here, the objective function is minimum time, I believe. And then start to finish, start at rest, end at rest. Don't fall in the hole. And you also can't get any contact forces. Great. So let's go back a step. We've created some trajectory or some controller using sub-method, maybe this, maybe the hybrid trajectory optimization. Now we have to actually get that to work on the robot. And so here's this is the output from some of the hybrid trajectory optimizations running on the robot. Again, what's this weird tail thing doing? What are we trying to learn with this? Go talk to Joe Norby or me later today, and we're happy to talk to you about tails. The point is that if we do good modeling and have a simple sort of trajectory tracking controller, we can get these behaviors to actually run on the robot. So we got this, we said, great, it looks like it's running really well. What if we go a little bit faster? Let's try and push this. And so now this is using the same model, the same trajectory optimization framework, the same tracking controller. We just tried to go slightly faster, and all of a sudden the robot flails around and can't do anything. And again, just like Shaw earlier, the problem really comes down to the feet are not on the ground when the model thinks they're on the ground. So if you looked at the motor tracking error, it would actually be pretty good. The legs are kind of going through the right motions. It's just that sometimes they're whiffing and missing the ground, and other times they're stubbing, tripping over their own feet. This is trajectory reference tracking. Okay, so the point here is that a lot of these sort of, you might call this transfer learning or sim to real, the models are end up being pretty brittle, and you have to have very good actuation and sort of full system models in order to do this kind of transfer. And so this is sort of ongoing work to improve this. So that was all about contact. What if we wanted to include notions of uncertainty in our trajectory optimization? And there's many ways to formulate this. I'm particular to these divergence metrics that come from contraction analysis. And the basic idea here, I'm not going to go into the math, basic idea is that we were going to look at however much uncertainty we have, is that growing or shrinking over time? And so this could be in a particular direction or a volume of uncertainty. We're just going to look at how that changes over time. And this lets us get a local measure. We don't have to say, I think we're going to have 1 centimeter of error. However much error we have, we'd like that to be reduced over the course of the trajectory. And so the application that we've applied this to that you can use later today is hill navigation without a GPS. So let's say we're out wandering in some terrain, hypothetically, and we don't have our GPS with us. How can we sort of reliably navigate? So for most robots and animals, actually, the walking uphill is actually unstable. We start walking uphill, and we would slowly peel off and go downhill. But it's pretty easy using only local information with an IMU to figure out where the hill gradient is. And then we can use the hill map as our compass to guide us to where we want to go. We can design a controller that's based on the angle relative to the uphill direction at every point along the way. And so how does uncertainty play into this hill climbing problem? Yeah. I think it's if you're going uphill and you've got legs, your center of mass is behind your legs, and you sort of peel off, but it's very hard to show for animals because you have to turn off all other sort of intent. Just say, just walk blindly and see where you go. But from the sort of, so yeah. In any case, it's very easy to then do closed loop control and stabilize the uphill direction. So how does uncertainty affect this hill climbing problem? So here we're showing just a pure walk uphill. This is literal gradient ascent with some initial uncertainty. We can see on the left, based on the shape of the terrain that we're walking on, this ends up being a diverging trajectory. While on the right, based on the shape of the terrain, we have a converging trajectory. So what we'd like to do is come up with plans that take advantage of converging paths to produce more reliable behavior. And so we can put these, we can quantify this convergence and divergence, put this into our trajectory optimization problem, come up with trajectories that might be a little bit longer than a straight line trajectory, but that end up being more robust. So here, let's say this is our start and end. If we drew a straight line from the start to the end, and looked at how some initial uncertainty translated into a final uncertainty, we get this huge blob because we're going in a very diverging region. With our trajectory optimization, we can now take this much longer path and end up with a smaller uncertainty at the end than we began.
Is this in the absence of a tracking controller, just a pure?
This is using just the local hill gradient, hill relative control. So it is feedback control, but we don't have global position. If you had global position, then just stabilize to the final position, and that's great.
And in your optimization, you're tuning both the feedback parameters and the trajectory, or?
Yes. So if you have more questions on this, Nathan Kong is over there. He talked about Flamingo yesterday, and he'd be happy to answer them. So for the rest of the time, which might be like 2 minutes or something, I wanted to just give a quick summary of a few projects in these other areas that we work on in the lab. And the first is sensor design. And so for this, I'll use our direct drive hand. So this is a collaboration with Matt Mason's group. So this is a 5-bar linkage, 2 degree of freedom per finger, direct drive servo gripper. And what we like about direct drive, both in legs and in fingers, is the transparency. And so because there's no gearbox, there's no reflected inertia, there's less friction, so we can be very transparent, very compliant with the environment. And what that gets us in terms of sensing is it gives us really good proprioceptive sensing. So we can feel the world without sort of knocking over everything that we touch. And so we designed this, we call this the smack and snatch, where we're going to accelerate the hand as fast as possible into the table. The fingers are transparent. They comply when we hit the table. We don't break the fingers. We don't break the table. And we're able to use proprioception. So this is using only the motor encoder. There's no tactile sensing. There's no force torque sensing. We're just feeling when we touch the table, closing the gripper. You can see here that we are now robust to significant uncertainty in where that table is. So these are all running the same controller. We have no idea where the table is. And so this kind of transparency in perception and proprioception makes us very robust to contact uncertainty. So one other perception project, my student Joe Payne, also known as John Payne, works on what we call shaky perception. So if you're sort of bouncing along on rough terrain, computer vision becomes much harder. If you're interested in computer vision, go talk to Joe Payne. All right, platform design. I'm not going to spend too long on platform design because I think you guys have already seen a lot of hardware design projects coming out of my lab. So go talk to Joe about the tails, the Flamingo bot you saw yesterday. That'll be at the hardware demo. But I couldn't give this talk without showing you one of the new toys in our lab. And so we're trying to make miniature humanoid robots in the sort of 2 to 4 centimeter scale. And what does that look like? It looks like a Lego minifigure that we want to walk. So how can we package up very small motors, very small electronics, and actually get something at this scale to walk stably? Obviously, right now, it is not very good at walking. It is not packaged up. And in fact, this is at 2x. So this is twice as big as the Lego minifig that you're picturing in your head. So a little sneak preview. Hopefully next year we'll show up with a walking Lego minifigure for you all to play with next year at Dynamic Walking. So in addition to thinking about the robot design, we also like to think about what is the environment that the robot is going to operate in, and what kind of models do we need of that environment. So for this, I'll use this terrain manipulation project. So here we want to not just get over rough terrain, but also modify the terrain as we can go. And so this is a sort of a Mars rover. You can see this back wheel is digging a trench as it's going along. And so you could imagine digging this trench so that you can sample soil at a lower depth, or maybe lay a buried cable, or I really want this guy to go back and forth many times, slowly build up a ramp, and then get out of this box that it's stuck in. So for this, we need to have better models of how the wheel and the sand are interacting. So we're taking classical terramechanics models and adding in some notion of how the soil flow around the wheel happens so that we can predict the shapes that we're creating. And then we can use those predictions to now do planning and control and learning to come up with these different sequences of behaviors. And finally, some of the sort of system level behaviors that we're interested in the lab. The first is rocky hill climbing. So what's the sort of steepest, roughest terrain we can get up, and what's the sort of limits of the type of navigable terrain we can cross. But I'm also really excited about it. We have a new project now in environmental monitoring. So in remote locations, can we send legged robots out to go monitor the environment for contaminants, pick up some dirt, see if there's oil or other contaminants in the environment, and try and get a better sense of this kind of environmental monitoring. So these are some of the sort of target behaviors we're looking at. So to recap, we're very interested in contact and uncertainty, and in particular how these two things interact to make locomotion and manipulation hard. And with that, I'll take some questions.
Michael, and then Jim.
So Scott and Zach Manchester, right, had some work on spec calculation where they were trying to get to higher order accuracy, and the challenge. So they got higher accuracy except when the contact mode was changing, when they fell back to first order. Did you dodge that issue as well, or did you have it kind of in the same somewhere?
So yeah, I took that slide out. They were.
Can you rephrase the question for us?
Yeah, the question was, Scott and Zach Manchester have a paper trying to get higher order accuracy with these contact-implicit methods, and I think the other details weren't important. I'd say that the difference there is that they were trying to take the dynamics and use higher order representations of the dynamics.
I think the details are important. So the question is basically, can you get higher order integration accuracy when the contact mode is changing, or around, in those DTs when you have mode changes, are you back to first order and you get higher order accuracy when the mode is consistent?
Yeah, so the contact mode is only changing at the boundary between finite elements. And so you could call it first order, but it's really whatever impact law you're enforcing. So rather than a continuity constraint between your finite elements, you have impact law that says my outgoing velocity must be consistent with my incoming velocity. It's not equal, it's now based on some impact law. So it's however accurate that is.
Sort of follow-up questions. So something about your algorithm ensures that the contact event happens only at a grid point,
Yes.
which ensures the higher order accuracy.
Yeah.
What can you explain in a sentence what that thing is about?
Yeah,
your
so
algorithm?
the complementarity that says you can't have force at a distance is enforced over the entire finite element. So if you have force at any point in that finite element, you have to be touching the entire time.
And in all your sort of trajectory optimizations, it is the fact, like you verified that the contact event does happen at a grid point.
Yes.
To high accuracy. And then presumably the order of accuracy of the optimization or integration can be verified empirically by doing a sequence of refined number of grid points.
Yeah. So let's see.
Sorry.
All right. I'm not going to go to the backup slides, but
Yeah.
so one thing we can do is to make the problem easier to solve, we can relax it and stretch the impulse over a finite element, and then we show in the paper that if you let the DTs go to 0, it actually does approach in the limit the sort of hybrid instantaneous transition. Getting to the other part of that, if I could, the Scott Zach's work was using higher order dynamics with then first order integration. And I think there's no reason you couldn't do higher order dynamics and integrate that with higher order integration.
I'm going to let Scott do a follow-up and then Jill. Yeah.
My question is about the video you had of the
Oh,
quadruped
different question.
doing the trajectory execution. Is it the case that the timing and even the sequence of the hybrid modes in that execution matches the plan, or are you taking advantage to some extent of the mechanical stability of a quadruped? You kind of just fall into the other lanes and keep going.
Yeah, there's a little bit of toe bounce and that kind of stuff, but it's pretty close. And we can look at either the leg tracking or the body tracking. I mean, it's not perfect. I don't have a plot showing exactly how close it is, but I mean, this one it's a bound, and Joe, this was the exact.
Yeah.
Yeah. So this one, I think we were saying, when you touch down, the other lifts off, and it's close certainly. It's definitely not exact.
Jill, a question there.
So yeah, I have two questions. One is actually follow up from Manoj and Mike's question.
Yeah.
So how did you actually determine the higher orders order? Which order did you use?
Yeah. So we've used third order and fifth order Pareto polynomials. There's lots of options for this. The nice thing is that we are now using, we now have sort of smooth systems in between the contexts, and so any of the results from traditional trajectory optimization on smooth systems carry over. And so we measure the accuracy. We use like a high tolerance ODE 45 integration afterwards to see how close the trajectory optimization got to a very accurate integration.
And my second question is, you use linear complementarity, and how did you actually get the force value which depends on the contact property?
How do we get the force value that depends on the contact property? So the constraints in the optimization include the dynamics, so your MQ double dot that includes the force, and then also the position constraints. So if it's touching, then it has to be zero position. So the force is however much force it needs so that it doesn't push through the ground.
Well, what about the elasticity and the damping properties for the contact?
So we don't have, I don't think we did anything with sort of like bouncing contact. So this is all plastic impact. And I kind of, anything, if you look at it close enough, will bounce. But I think it's a pretty good approximation that when I put my hand on the table, it's not bouncing. So I prefer plastic impact anyway. But that's definitely, the assumption here.
Carlota?
Hi. In your biped solution, the sneak peek, given that is most likely a local optimal solution, right?
For the biped running?
Yeah. So my question is, when do you say that, okay, I'm happy with this solution? Or again,
Yeah.
how do you validate this solution other than qualitatively?
Yeah, it's, I'm sure we're in a local optimum. I don't know how local is local. And especially with the sort of, we've taken an inherently discontinuous problem, we've formulated it in a way that smooth solvers can handle, but the underlying dynamics really are discontinuous. And so, so it's sort of very solver dependent how it navigates between sort of different possible solutions. And with this sort of method, I don't have a good way of saying this was the best and if you initialize it somewhere else. I can tell you the initialization here, I think we took the body perfectly vertical, and did a linear interpolation across. I don't think we needed to do that because that's the easy part, right? The optimization will figure out that the body needs to end up over there. So it's more about like which contacts along the way.
The next speaker should probably start setting up while we take a few more questions. Andy?
In the end, your optimization calculation at best has first order fidelity to the simulation because your contacts are not going to line up when you in the real system to the optimization calculation. So why is it that getting high order accurate optimization is more accurate than the fidelity of your model can possibly be?
No, it's actually that the first order optimization is less accurate than your model, right? It's that it's approximating your MQ double dot or whatever your dynamics are with n individual samples. And
there's
if
a
you,
misunderstanding of the question.
Do you want to translate, please?
Andy is saying, okay, you can do this higher order optimization on your model, but then when you implement it in the robot's impacts are not going to line up with your grid points anyway because of small uncertainties. So your robot will not match your model to any greater accuracy than first order.
Yeah. So that did not, the trajectory, the contact-implicit stuff did not address that problem.
No, but
It
so
was
why,
sim-
what's the intuition about why you need an accurate optimizer when your simulation is already as good as it can be?
When compared to the robot.
Compared to the robot.
So if we did higher accuracy simulation, meaning forward integration, it would be accurate. But with trajectory optimization, we only have whatever accuracy in terms of the number of grid points. So basically, it's lower accuracy than the underlying model, because it's a numerical approximation based on some number of points. And if it's first order, then it goes with 1 over n, 1 over the number of points. If it's higher, it's 1 over n to some exponent that includes the order. And so it actually scales very favorably with these higher order. This is like standard sort of numerical integration result. that you
I
want to use.
understood the last phrase, but I didn't answer my question for me, so we can talk later.
I tried this once with an Acrobot using first order integration and trajectory optimization in simulation. You can use 100 knot points to Acrobot swing up, and then you cannot stabilize it easily with LQR. If your nominal trajectory for underactivated system is inaccurate. And that was surprising to me. I think it would be surprising to a lot of people.
Well, there's different levels of inaccuracy, I guess.
This is like,
Maybe first order integration is horrible, but third order integration is good except for the, like if you just go wrong at the impacts, then maybe it's okay.
yeah, or like, a simple example, let's say you wanted to run in a circle, but you could only take 10 steps or 20 steps, let's say, in the circle, but they had to be perfectly straight, right? As you go along, if you're tangent at each point, you're going to slowly get off of that circle. That's the sort of inaccuracy that we're capturing. It's not that the dynamical model would say you're going to drive in a circle, and when you do first order integration of that, you'll get these discrete steps that are a low accuracy approximation of those dynamics.
One last remark by Scott.
One more clarifying
Yeah.
thing, with these optimizations, the time delta is much, much larger than you'd ever use in simulation, because you can only solve an optimization of a certain size. So that's all.
Art, did you have a remark? Or question?
I just wanted to try to translate. I think the issue is not first order. The issue is forward Euler is bad. I think that's all there is to it.
No, it's a different.
It's implicit Euler.
Scott answered my question. It's that there's 2 different time steps in the optimization and in the simulation. And since they're using such big time steps in the optimization to match the first order real world, more or less, they need to take a higher order method. If there were equal time steps in the optimization and the simulation, then I think my question would go away and there wouldn't be an issue. So you're taking larger time steps in your optimization.
I think even in simulation, you still use something like ODE 45 that's using higher order approximations than implicit Euler.
Not if you're using an
Or not in time step. That's, yeah. All right.
Okay, let's thank Aaron again.